India is highly vulnerable to extreme weather events such as cyclones, floods, heat waves, droughts, and landslides due to its diverse geography, long coastline, and monsoon-dependent climate. According to the India Meteorological Department and the Ministry of Earth Sciences, India experiences hundreds of extreme weather events every year, with floods affecting nearly 40 million hectares of land and heat waves becoming more frequent in recent decades. Over 75% of India's districts are exposed to multiple climate hazards, while cyclones and floods account for a large share of disaster-related losses, according to the Council on Energy, Environment, and Water. In this context, early warning systems have become a critical tool for disaster risk reduction and climate resilience in India. About early warning systems. An early warning system, EWS, is a system that helps in detecting a possible hazard in advance, predicting its impact, and informing people in time so that they can take protective action before the disaster occurs. The United Nations Office for Disaster Risk Reduction defines early warning systems as a set of capacities and procedures for generating and disseminating timely and meaningful warning information to allow people exposed to a hazard to prepare and act appropriately. Components of an early warning systems. An early warning system, EWS, is not a single tool or technology. It is a chain of interconnected processes that work together to ensure that a hazard is detected early and people respond in time. According to the widely accepted framework used by the United Nations and disaster management agencies, an effective early warning system has 4 essential components. Risk knowledge. It refers to systematic understanding of hazards, exposure, and vulnerability in a region. For example, coastal Odisha and Andhra Pradesh are identified as high cyclone risk zones, while Bihar and Assam are mapped as flood-prone regions due to recurring river flooding. Monitoring and forecasting. It is the continuous scientific observation of environmental and geophysical conditions using tools such as satellites, radars, and sensors to detect hazards early and predict their likely intensity, location, and timing. Warning communication and dissemination. It involves transmitting risk information in a timely and understandable form to authorities and the public through channels like mobile alerts, media, sirens, and local administration so that people receive actionable warnings. Response capability. It is the ability of institutions and communities to act on warnings through preparedness measures such as evacuation, emergency planning, and coordinated disaster response to reduce actual loss and damage. Early warning systems types. Early warning systems can be classified in different ways depending on the nature of hazard, scale of operation, approach, and technology used. Based on hazard type, hydrometeorological systems cover cyclones, floods, heat waves, and droughts. Geological systems cover earthquakes, tsunamis, and landslides. Biological systems cover disease outbreaks, and environmental systems cover forest fires and air pollution. Based on scale, global systems operate across regions or countries. National systems function within a country like India Meteorological Department alerts, and local systems operate at community or village level. Based on approach, single hazard systems deal with one disaster type, while multi-hazard systems integrate multiple hazards in one platform. Based on technology, systems range from traditional observation-based methods to satellite and radar-based systems, and now to AI-based predictive systems. Early warning system benefits. Early warning systems play a crucial role in reducing disaster impacts by enabling timely preparedness and response. Saving lives. Early alerts allow timely evacuation and significantly reduce mortality during disasters such as cyclones and floods. Reducing economic losses. Advance warnings help protect crops, infrastructure, and property from large-scale damage. Improving disaster preparedness. Governments and communities can plan evacuation, resource deployment, and emergency response in advance. Supporting climate adaptation. Early warnings help societies adjust to increasing frequency and intensity of extreme weather events. Strengthening governance. They improve coordination between central, state, and local authorities during emergencies. Empowering communities. timely and understandable alerts enable people to take informed and immediate protective action. Status of early warning systems in India. India has developed one of the most advanced early warning system frameworks among developing countries, particularly for cyclones, floods, heat waves, droughts, and tsunamis. Over time, the system has evolved from fragmented and sector-specific forecasting to an integrated, technology-driven, and increasingly impact-based warning system, improving disaster preparedness and reducing losses. Institutional framework. India's early warning system is supported by a strong multi-agency setup. India Meteorological Department, IMD, issues forecasts and warnings for cyclones, rainfall, heat waves, and extreme weather events. Central Water Commission, CWC, provides flood forecasting and river level monitoring. Indian National Center for Ocean Information Services, INCOI, manages tsunami early warning and ocean state forecasting. National Disaster Management Authority, NDMA, coordinates disaster preparedness and national alert systems. Indian Space Research Organization, ISRO, provides satellite-based observation and forecasting support. Technological advancements. India has significantly strengthened its warning systems through modern technologies. Multi-hazard integrated systems. India is developing platforms that combine cyclone, flood, heat wave, and rainfall forecasts into a single decision support system for faster and coordinated action. Impact-based forecasting. The focus has shifted from only predicting weather to assessing who will be affected, what damage may occur, and which areas need evacuation, enabling targeted response. Satellite and radar expansion. A wider Doppler radar network, satellite systems, and ocean buoys have improved real-time tracking of cyclones, rainfall, and ocean conditions. Digital alert systems, mobile SMS alerts, the NDMA Sachet application, and media-based warnings ensure faster dissemination of alerts in multiple languages. Advanced flood and urban systems, 7-day flood forecasts, 72-hour city-level rainfall alerts, and AI-based monitoring for glacial lake outburst floods in the Himalayas have strengthened regional preparedness. Financial and institutional investment. The government has invested significantly in strengthening forecasting infrastructure, with over 2,300 Indian rupees crore spent on early warning systems since 2014, indicating sustained capacity building in disaster prediction technologies. Key implementation challenges. Despite significant technological and institutional progress, India's early warning system continues to face several structural and operational challenges that limit its full effectiveness. Last-mile communication gaps. Reaching remote, tribal, and hilly regions remains difficult due to weak digital connectivity and infrastructure constraints. Uneven community preparedness. Awareness levels and disaster response capacity vary widely across regions, limiting effective action even when warnings are issued. Institutional coordination issues. Delays and overlaps in coordination between central, state, and district-level agencies sometimes affect timely response. Urban vulnerability in informal settlements. High-density informal urban areas often lack preparedness systems, evacuation planning, and structured communication channels. Data integration and standardization issues. Despite technological progress, integration of real-time data across multiple agencies and platforms remains inconsistent.